We'll proceed in the product rule of the calculus. Okay, so main idea is to main idea is main idea is to demonstrate the concept of chain rule, that is integration by part, because integration, we consider integration as the building block or main item, integration being the base item for the calculus. So idea is how we can go, how we can okay, so idea is how we can do integration by part. So in calculus there is integration by part, that is the way we go with the chain rule in the integration. So if that is the case, then how we can achieve integration by part in calculus? For that we started kind of, it is called product rule in differentiation. Product rule in differentiation. If I have two functions fx and gx, fx and gx, if they are multiplied by each other, fx into gx. What is differentiation of fx into gx? Differentiation of fx into gx. d fx gx by dx. What is that? Then it is fx dgx by dx plus gx dfx by dx. This is called product rule. How we can come to this product rule? Integration by part in the integration is, we can consider that it is extension of this product rule. Or if I know integration by part in integration by part or chain rule in integration, then we can come to product rule. As integration and differentiation, it is kind of complementary to each other. If I know one, then other I can get. So if I know product rule, I can get chain rule or integration by part. If I can prove integration by part, then I can prove the product rule in differentiation. Let's prove the product rule in differentiation so that I can prove the integration by part. This way, I am trying to say other way. So I have to prove differentiation of fx into gx, differentiation of fx into gx, dfx into gx by dx equal to fx dgx by dx plus gx dfx by dx. So this is the product rule in differentiation. How to prove it? One proof that we saw, that since I have to calculate derivative of fx into gx, fx into gx, if there are two functions, they are multiplied together, then if I have an area of a rectangle, then I have to multiply the two sides of the rectangle to get the area. This is the general concept. If I have area of a rectangle, if I have area of a rectangle, I know area of a rectangle. If I have area of a rectangle, then how I can achieve the area of rectangle is to multiply one side with other side. If area of a rectangle is fx into gx, this proves that one side is gx and one side is fx. In reverse way, if I multiply two sides of a rectangle fx and gx, that is fx into gx, it becomes area. If I have an area that is fx into gx, this proves that one side is gx and one side is fx. This is what we saw. dfx into gx by dx. If I want to calculate the differentiation, then consider fx into gx is area. What consideration? I mean, this is what is actually it is. But if fx and gx are there, then independent component is x. fx function over x and gx function over x. Independent component is x. Now consider, or I have considered area at fx into gx. d area by dx. If d area by dx means if I do one unit of change in x, if I do 1 unit of change in x, how many unit of change that is seen in area? That is dA by dx. So if I make 1 unit of change in x, then how many unit of change that is seen in area? That is seen in area means that is meter square. If it is meter, x is meter, then A is meter square, dA by dx, meter square. If that is the case, then consider dA by dx equal to delta A. dA by dx equal to delta A. Okay, means if I make delta x change in A, if I make delta x change in x, then how much change we see in A? Consider that is delta A. Okay, so that consider that per unit change in x brings delta A change. If there it is delta A, dA by dx equal to delta A, then delta A can be considered as summation of two areas. Any area I can consider summation of two areas. Delta A1 plus delta A2. Delta A1 that is part of, now we have two functions. One is gx and one is fx. So the delta A1 is part of gx and delta A2 is part of fx. One is part of gx and one is part of fx. Okay, delta A part of gx plus delta A part of fx. So the gx part is, we consider delta A. So if this is gx, then the area that belongs to the change in area, this is anyway full phase area. Along the gx, what area we see that would change is here, okay, or here. That is along gx, this much area, this is delta A1. This is the area that is changing when that is delta A1. So delta A1 is share. Now if I say if there is a change in area, then area change is kind of, it has share for the change in gx and it has share for change in fx. But if you see the book, then they describe that if I have dgx into fx by dx, and if that is the case, then consider that result into some amount, okay, that result into some delta exchange for the fx and delta y change for the fx. Means there is some change. If I say I mean reiterating, if I say dfx into d of fx into gx by dx, if I do unit change along x, then how much change that is seen in the product of fx and gx? Okay, so consider that is some amount. Some amount, if I see, then there is, now it is written in the book, this is the concept. Then consider that that amount has proportional, that amount along the is in two axes. One is along vertical, that amount is changed. So this area grew by this much along this axis and this much along this axis. So this delta is called change, because in gx, this gx has this much incremental. If dgx fx by dx, it brings some difference. If there is a unit change in x, then that difference is nothing but one small delta x difference along gx and delta y difference along fx. So fx grew by little bit because there is change in delta A, right? A has changed. If A has changed, means there is some amount that is added along this side, some amount that is added along this side, x-axis, y-axis. So this side some amount added and this side some amount added. If that is the case, then this amount what is added, this amount what is added, if this is gx, then dgx by dx. That is the amount that is added here. Because at the end, what amount we are talking is d gx fx by dx. So it has share as dgx by x and it has share as dfx by x. So dgx by x, they call it, that is the amount that grew here. dfx by x, that is the amount that grew here. So then what about if I draw it, then it will become like a, there is a line like this. There is a some strip like this. That is d gx by x or d gx by x. That is the amount that I see grew along this side. Okay, and this side, this is fx, then fx grew by dfx by dx, because at the end what grew is dfx gx by dx. If that is the case, if that is the case then if that is the case, then if this side it grew delta y and this side it grew delta x, then there is at the corner, there is a small section where the area is dgx by dx into dfx by dx. If this width is dgx by dgx by dx, where this length is gx and this height is fx, then this width is dfx by dx, then what is this area that grew? Then it is this height into width. If I am talking about how much it grew, if I say dgx into fx by dx, that is nothing but if I do 1 unit of change in x variable, how many unit of change I am seeing as a multiplication of gx and fx. This is what we want to calculate. If that is the change that we are seeing, if that is the change we are seeing, then how much, if I know dgx into fx by dx, then what is the share for the d gx by dx and dfx by dx? So that share, if this is gx, then that amount that grew in the area, then that width, this width is dgx by dx. This height is dfx by dx, and this corner portion is dgx by dx into dfx by dx. So how much area got incremented? That is the question. If I say there is a strip added along gx because of this differentiation, and there is a strip added along fx because of the differentiation. This strip and this strip at the corner, they make a small area. So net area along this is height into width. So fx into dgx by dx. Here gx into height, dfx gx into dfx by dx. So net is fx into dgx by dx plus gx dfx by dx plus this corner dfx by dx into dgx by dx. Since they are very small, so tends to 0. So dfx into gx by dx, where gx and fx are side of a rectangle whose area is gx into fx, then this differentiation is nothing but how much, differentiation means how much, what is the rate of change that is seen in this multiplication with the x variable. So that rate change is this strip plus this strip plus this strip. This is nothing but fx, this is nothing but fx into dgx by dx, and this is gx dfx by dx, and plus this dfx by dx into dgx by dx. If that is the case, then this corner one is gone, because dfx by dx, that if delta x, dfx by dx is nothing but delta fx by delta x, delta fx by delta x. Considering delta x tends to 0, then delta fx also tends to 0. If that is the case, then this portion is gone. So what change in area, what we are seeing is this portion and this portion. Because this portion had fx that is very big, so fx into dgx by dx will be considerable amount. Here gx is very big, so gx into dfx by dx is considerable amount. So dfx into dx by dx equal to gx dfx by dx plus fx dgx by dx. This is you find in the book. We are not satisfied with this answer. This is what we are reiterating. So what we are saying that consider gx into fx is area, dA by dx equal to delta x sum change. Just consider everything through area only. Don't go with the with the x-axis change and y-axis change. If you make x-axis change and y-axis change, you get the corner where you have approximation. So go with the area. If it is delta A is A1 plus A2, then A1 is area change along fx and A2 is area change along gx. If this is fx, then area change is this much. If this is gx, then area change is this much. Okay, then in this explanation we don't talk about the corner at all. If you go by the area, if you go by the x-axis and y-axis, that's why you always reiterate that keep things minimum. If you have x-axis and y-axis, then don't consider two independent variable x and y. Consider single independent variable as xy plane. Single independent variable as xy plane. If that is the case, then I have single thing, that is area. Two area. One is along fx and one is along gx. So area along fx is this much. Up from here to here, no corner is making. Area along gx is this much. So this area is gx into whatever this area is. Okay, so this area is this area is gx into whatever the change we saw. So that is gx into dfx by dx. Okay, I believe I tilted it. Okay, so this area belongs to how much? How much? A1 plus A2. So this is A1 and this is A2. Area, okay, this is Fx and this is Gx. Consider that Fx side got the area. So Fx side get the area, then this is the area. Gx got the area, then this is the area. For the Gx, the area is Gx into dfx by dx, and here the area is fx into dgx by dx. This is how it is. Probably we will talk on this more, but we have to proceed through area wise one. That is the key concept. So someone can think other way, that this area belongs to fx. If this area belongs to fx, then this height is dfx by dx. And if this area belongs to gx, then this width is dgx by dx. So whatever it is, we'll talk more on it. But concept is, don't go with the, if you have two independent things, one is x-axis and y-axis, and makes a rectangle, this is xy plane or gx-fx plane. Gx-fx plane. If you have this kind of situation, then go with the xy plane. Don't go with the x-axis and y-axis separately. This is what people they do. If they have function fx gx, consider fx gx, one is x-axis and y-axis, then in that case, then whatever the change in area is seen, now they consider that one change is along x-axis, one change in along y-axis. That's why we have this strip and this strip, and there is a corner. If that is the case, then this area plus this area is the net differentiation, and this corner we can take it out. No. Consider that we are differentiating the xy plane. If we are differentiating the xy plane, then along one side, that is this side, there is a growth that is seen, or there is a growth. No, I think this is better now. Along this side, there is a growth that is seen, and along this side, there is a growth that is seen. No, I believe we were earlier better. This is what we are proposing. This is what we are proposing. So work is required. So if I go with the area fundamental, whatever the if this has, if this is the area, and because of there is a change in x, there is a delta A area change. This delta A area, if I divide, then along one side there is a delta A1 change, and along other side there is a delta A2 change. What is this and what is this? Okay, then this is fx into dgx by dgx by x. This is what we are saying, and this is nothing but gx into dfx by dx. We will see it, but whatever it is, we have, if I go with the area fundamental, then area growth can happen only along this side and only along this side. So area growth cannot happen in the corner. If this is area, then area has two sides, one along this side and one along this side. This area I can think of as a strip, one strip, two strip, three strip, four strip, or a strip like this, one strip, two strip, three strip, four strip cannot go in this direction. So one strip it goes, one strip is this, their area got elongated, and one strip is this where area got elongated. This is not required. So this is dfx gx by dx equal to dfx by dx into gx plus fx into dgx by dx. We will talk more on it. Why these are important? These are building block of extensibility of the calculus. So this is highly required. What about through first principle? First principle says that if you want to calculate the differentiation of fx, then fx plus delta x minus fx by delta x. If that is the case, then differentiation of fx gx is fx plus delta x gx plus delta x minus fx gx by delta x. Let's introduce something called g plus gx plus delta x fx, gx plus delta x fx minus g. If I introduce gx plus delta x into fx in the numerator, then I have to introduce minus gx plus delta x fx, then they will cut to 0. So let's introduce gx plus delta x fx minus fx plus delta x gx. If I introduce this, then first term fx plus delta x gx plus delta x, now we have minus gx plus delta x fx plus gx plus delta x fx and then minus fx gx. First, if I take it out, it becomes gx plus delta x in bracket fx plus delta x minus fx, and then another term, this is first term, another term becomes plus, then fx if I keep outside, then it becomes gx plus delta x minus gx divided by delta x. If I break it, then it becomes gx plus delta x fx plus delta x minus fx by delta x plus fx gx plus delta x minus gx divided by delta x. Then it becomes gx plus delta x into dfx by dx, that is fx plus delta x minus fx by delta x dfx by dx plus fx dgx by dx. Mind it, it is gx plus delta x into fx by dx plus fx into dgx by dx. If delta x tends to 0, then gx plus delta x also tends to 0. This is what we don't like. Approximation you can do, but approximation should vanish naturally. At the end, don't start estimating it tends to 0, it tends to 0. So I am taking it off. So first principle, disagree. Area computation where corner is delta x and delta y, that section becomes 0, it is not agreed. Area way we can take that area along f axis it grew this much and area along gx it grew this much. Now I have to check what is the height this much so that gx into that height would be the area and what is the width here so that fx into that is the area. In that fashion corner does not come. But still many people would not satisfy with this also. That how you can assume that area change along this side only, area change along that side only. Okay, let's go with the another proof. Now what you will see in the book that is called chain rule. Chain rule means differentiation of gx and fx. If I go by chain rule, then it is gx into dfx by dx plus fx into dgx by dx. Straightforward, people prove it. Chain rule, chain rule means differentiation of u and v. U is one function, v is one function. D of u into v is u dv by u dv plus v du. Okay, this is chain rule. This is again under question mark. How it is? Okay, we will prove it how it is. Then we will go with many proofs. Okay, consider xy plane. If it is xy plane, then this is x-axis and this is y-axis. If that is the case, then any point on xy plane is x comma y. If any point is x comma y, then function over x comma y is called fxy. That is z. So z equal to fxy. What is dz by dx? What is dz by dx? What is z? What is z? How much is the z? Okay, what is this? This is dfx. If this is x-axis, this is xy plane, then keep this xy plane as it is. I consider there is a surface that is kept on the xy plane where this is x-axis, this is x-axis from my side, and this is y-axis. This is a plane that is kept on the xy plane, xy surface. If this plane is kept on xy surface, then this, if I tilt the surface like this, then this slope is dfx by dx. If I multiply this slope with any x, then it gives me net z that got incremented at any point xy. Consider there is a point xy here. Okay, if I say dz by dx or dfxy by dx, then partial derivative along x-axis. It talks about the slope. If this is the x, this not full. If this is the x somewhere here, then dz by dx into x give me the net z that got incremented at point x and y. Now, if this is the case, now we tilt in y direction also. This is dfxy by dy. Then at that point, how much is the increment again? There is one, earlier it was like this. There is one increment because of dfxy by dx. There is another increment at that point in z, that is dfxy by dy. How much is the net increment at any point x comma y? That is addition. One is this much and then again then add this much. That is the z at x comma y, that is z at x comma y or fxy equal to dfxy by dx into x at point x. If you consider x0, then dfxy by dx, this differentiation when x equal to x0 into x0 plus dfxy by dy at y equal to y0 into y0. That is the z at that position, or we can say z equal to dz by dx into x plus dz by dy into y. Dz by dx is the partial derivative along x-axis. If I multiply this slope at particular x, it gives me the height. And then if I do partial derivative along y-axis and then multiply by the y, then net y how much increase? If I add both, then at any point x comma y, from here to here, how much is the z I can see, that is z equal to dfxy by dx into x plus dfxy by dy into y. This proof again is not available anywhere else. Please support us. Okay? Please support us at +91, that is India code 94831 60610. +91, that is India code 94831 60610. Okay, now z equal to dz by dx into x plus dz by dy into y. Now z is function over x and y. Here we have function over gx and fx. Gx and fx. Okay, gx and fx, or u and v. Dz by dx, d gx into fx, function over gx and fx. One we can consider x component and one we can consider y component, because they are multiple, so they are two sides of an orthogonal plane. If that is the case, then dz by dx into x plus dz by dy into y. If z equal to gx into fx, if z equal to gx into fx, then we have dz, that is gx into fx equal to dz by dx into x plus dz by dy into y. What is d of fx into gx, or d of z, or delta z? If z equal to dz by dx into x plus dz by dy into y, what is delta z? Delta z equal to dz by dx into delta x gradient. If z equal to this, then what is gradient? Delta z equal to dz by dx into delta x plus dz by dy into delta y. Delta z is nothing but d of gx and fx, where delta x is nothing but d of gx, and delta y is nothing but d of fx. So d of gx and fx, that is gradient, equal to dz by dx. dz, z is gx into fx, where x, two components. So x by dx, x is first component. So first component is x-axis is gx. So d of fx into gx by dgx. Gx, if I cut down, it comes to fx. So fx into dgx by dx plus dz by dy. dgx into fx by dy. Y is fx. dfx into dx. dfx into gx by dfx. It comes to gx. gx into dfx by dx. So d of gx into fx equal to gx d of fx d of gx plus gx d of fx. This is solid proof. And whatever the we have taken z equal to dz by dx into x plus dz by dy into y, this can be considered through Taylor series of the any polynomial approximation of any function as far as first order is concerned. Area proof also we will make it solid. So we have two proof now. One is through Taylor series, first order, that we saw now, and area proof. We will have three more proof where we will prove the product rule of the differentiation. So this is really nice one. So we will proceed on it.